All right there, class. We are here today to look at an example. This is example 2 from our physics notes. And basically we have this box being pushed 25 meters along a horizontal surface by a hand. And this hand pushes with an amount of 40 newtons. And we want to know how much work is being done on the box by the hand. So basically, I'm going to show a picture here to kind of show I know what's going on. And what I have here is this applied force of 40 newtons, and that's pushing on this box. We have the gravity pulling down, some unknown amount, and there has to be some kind of opposing force to keep this thing from falling down through the floor, and that would be the normal force pushing up because of the surface. Now this problem doesn't say anything about friction, and you'll see in a little bit that that's not going to actually matter anyway. So looking at this more from a kinematics and energy standpoint, basically we have our object moving here, the 25 meters. Assuming there's no friction, this will actually accelerate at some unknown amount. And as far as energy goes, what would happen here is we're going to start with some amount of energy, 1/2 mv squared. Whoops. That would be initial velocity squared, and some mgh worth of potential energy. Now what we need to remember is that work can do a couple things. Work can be done against opposing forces. Work can change the energy of a system. And these are going to give us some different approaches to look at this throughout our study of work and energy. I guess one could say that probably in this case, if we assumed there was no friction, then this kinetic energy at the end would be larger. So the work that we're doing here, which is that's actually what we're trying to find. So this is our find, is going to actually change the work. The work we're doing is going to actually change the kinetic energy here. The potential energy, because it's a horizontal floor, is going to be the same. So that's an unchanged value. So one approach would be to look at how does this work change the kinetic energy. The problem is we don't know how fast it was going, we don't know its acceleration, and we don't know how fast it's going at the end. So this approach is going to lead us down kind of a rabbit hole where we're not going to be able to get out of. So I would propose we look at this a little differently. That our strategy here is work. There is an equation for that, and our work is taken by taking the force that we apply to something times its displacement that is being caused by that. So if we want to know the work done by the hand, the applied force was the work done, or sorry, the force that does this work, and then delta x is the displacement that undergoes because of this work. So pretty much, this is a pretty straightforward calculation. We are going to substitute in, tell you what, let me get a different color. Let me get black for this. Basically, we're going to substitute in the force, which was the positive 40 newtons, and we're going to multiply that by the displacement, which I do forget. I think it was 25 meters, but let me just go up here and check. Sure enough, there it is, 25 meters. And again, I have a positive 25 meters. I guess I'll lift the units out. And when you actually end up doing the math of this, 40 times 25 is actually going to give you 1,000. And the units for work is in joules. As long as you have your force in newtons and your distance or displacement in meters, you're going to get joules. So to respond to this particular problem, the work done in this particular problem is going to be 1,000 joules. Now in future problems, we will see there are different approaches. I mentioned to you earlier here that one thing that work can do is it can actually change the energy of a system. And again, maybe in this case it does, maybe it doesn't. We really don't know enough about what's going on with the forces to actually know this. But in the end, we are given enough information to simply apply the work equation to actually find work.